Hi Professor, my name is Vishnu. I along with Vivek have built a chatbot and we would like to go over the background of the chatbots, data we used for this project, prior work we reviewed, the approach we followed, the results from the chatbot, and finally the challenges that we faced during the total process. Having said that, let me give you a little background of chatbots. From Eliza to Alexa. Eliza was the very first chatbot which was created by Joseph Weizenbaum in 1966, which uses pattern matching and substitution methodology to simulate conversation. Next is Parry, which was constructed by American psychiatrist Kenneth Colby in 1972. Next comes Jabberwocky, which was created by developer Rollo Carpenter in 1988. Next comes Dr. Spatzo, which was created by Creative Labs for MS-DOS in 1992. Next is Alice, which is a universal language processing chatbot that uses pattern matching to carry conversations. Next is the Smarter Child, which in many ways is a precursor to Siri in 2012, and it was developed in 2001. Next comes Siri, which was formed by Apple for iOS in 2010. Next is Google Now, which was launched at Google Inch in 2012. Next comes Cortana, which is first demonstrated at Microsoft's Build 2014 developer conference for Windows 10. Next is Alexa, which is an intelligent personal assistant developed by Amazon, and it was introduced in 2014. Now let's see at our problem statement, which says that building a sequence-to-sequence chatbot with attention mechanism using Cornell movie dialog corpus data. So this problem falls under natural language generation problem, and to be more specific, it is a question answer problem. So there are primarily two different types of chatbots. One is a transactional chatbot and other is a conversational chatbot. So a transactional chatbot is pre-designed to provide a customer with a fixed set of choices. So a customer can select an option that is relevant to what they want to do, or what problem they want to solve. On the other hand, conversational chatbot is designed to understand and respond to a conversation in a natural human-like manner. To be able to do this, the chatbot is equipped with artificial intelligence and access to knowledge and other information, so to become more contextually aware. So once it is contextually aware, it can pick up variations in customers' questions and can give relevant answers in a more human-like way. And our problem statement is nothing but building a conversational chatbot. And some of the use cases of this chatbot include answering questions and inquiries, book tickets to events or shows, etc. Now let's look at our data. There are two data files that were used for this project. They are movielines.txt file and movieconversations.txt file. The movielines.txt file contains the actual text of each utterance. When you see the columns inside this particular file, there is a line ID, a character ID, a movie ID, in which movie is this particular dialogue from, character name, and in the dialogue itself, or the text of the utterance. The second file is a movie conversations.txt file, which shows the structure of the conversations. So when you see the data, so there is a character ID of the first character ID of the second character involved in that particular conversation, a movie ID of the movie in which the conversation occurred, and list of utterances that make up the total conversation. And also when you see the data, there are around 220k conversational exchanges that happen between around 10k pairs of movie characters. There are about 9,000 characters from 617 movies, and in total there are about 304k utterances in total. Now I would ask Vivek to talk about the prior work we reviewed and also the approach we followed.
We were checking for research papers on Chatbot and stumbled upon a research paper which discusses different methods and their challenges on a subset of this dataset. The first method talks about sequence to sequence and how its encoder-decoder architecture helps in sequence generation. Here, the encoder takes a sequence or a sentence as input and processes one word at each time step. Its objective is to convert a sequence of symbols into a fixed-size vector feature that encodes only the important information in the sequence while losing unnecessary information. Each hidden state influences the next hidden state, and the final hidden state can be seen as summary of the sequence. This state is called the context vector from which the decoder generates another sequence, one word at a time. At each time step, the decoder is influenced by the context and the previously generated symbols. But it has its limitations. In case of long sequences, there is a high probability that the initial context has been lost by the end of the sequence. Next, the paper talks about attention mechanism. The basic idea of attention mechanism is to avoid attempting to learn a single vector representation for each sentence. Instead, it pays attention to specific input vectors of the input sequence based on the attention weights. At every decoding step, the decoder will be informed how much attention needs to be paid to each input word using a set of attention weights. Next is Google Neural Machine Translation. As for this, it uses a similar idea as attention, but has a large number of layers, almost 8 on the encoder and 8 on decoder. They also use reinforcement learning with sequence to sequence, which we won't be discussing over here. The paper also talks about various limitations on chatbots. Most of the chatbots are limited in functionality and domain. They may not perform so well in long conversations and have reduced relevancy in dialogue generation. Sometimes the responses can be generic and same irrespective of the input and can get stuck in a loop. They are also black box as clients have limited knowledge of their architecture. So based on this paper and the data, here is the approach that we followed. First is the data pre-processing, where we start by cleaning the data like am to I am or haven't to have not. Then we store the question and their replies separately. Since the model may not perform well on longer sentences, we had set a minimum and maximum threshold for sentence length. We couldn't use the whole data as it was computationally expensive, so we used only a subset of it. We split the data into training and testing, 80% for training and remaining for testing. We built vocabulary and removed rare words as well. As for model building, initially we tried without the attention and the results were not so good for long sequences, as using a fixed dimension vector for encoding the whole input sequence is not capable of capturing the whole information. Then we tried attention mechanism and we were able to get good results. There are two types of popular attention mechanisms. One is Bahdana, another one is Luong. Bahdana uses concatenation of the forward and backward hidden states in the bidirectional encoder and previous target's hidden states in their unidirectional decoder. Luong attention uses hidden states at the top LSTM layers in both encoder and decoder. Luong is faster as simple matrix multiplication makes it faster and more space efficient. Bahdana is additive operation and takes longer to run. Here we have used Luong attention. The next is model running. Initially we tried with Google Colab. For training a sample of 1K sample using Google Colab, it took about 5 hours to run. Then we researched about the different GPU options like AWS and GCP. And finally we chose Floyd Hub GPU services to train our model. For the final model, we used 100K samples and the total time to train the model was about 4 hours. We tried various different hyperparameters to tune the model, and the following gave us the best results. In order to validate the output, we used BlueScore to compare the generated output with the original answer, which Vishnu will be explaining in the next few slides.
Thanks, Vivek. So now let's look at the results of our baseline model. For the initial baseline model, we had used only 1000 records since we were training on Google Colab and were facing many memory issues. So the hyperparameters we used were as following. We used a TensorFlow version 1.0, epochs 10, size of batch is 64, RNN size of 512, a number of layers 3, and so on. So here, as we can observe, no matter what the input, the output always seemed constant. The training this model consumed around 4 to 5 hours on Google Colab GPU. So when we gave issue OK, the chatbot returned out. With a different question, the answer was the same. How are you? It gave us out, and the padded sequence. Isn't the weather lovely? There was a similar answer for this. Since we had used only a few records for the baseline model, we decided to try with more data and different sets of hyperparameters in a different GPU environment. So we shifted to Floyd Hub GPU and increased the number of records to 100,000. So here a few sample records for the data are being randomly chosen and given as an input to the model. This model performed better than the baseline model. So here are some of the input sequences. How long does this go on? I do not know, either 8 or 9. Please hurry, I will do anything to help you. These are some of the outputs from the chatbot. Here's some of the input sentences are too vague for the model to learn the context. So we had tried giving in our own generic input sentences. So when we tried giving how are you, the chatbot gave us an output saying fine, I am fine, how are you? I'm good, thank you. Look, you are the same. Of course I'm the same. You are not. So we just tried to make a conversation with the chatbot. It was good enough, but we should say that this is very better when compared to that of the baseline model. And the hyperparameters that we used for this final model are embedding size of 128, hidden states in each LSTM is 512, and we used an Adam optimizer, and a loss as binary cross entropy loss with a batch size of 64 and number of epochs as 100. So as for the model evaluation, we had used the blue score metric, but one of the issues we faced while evaluating the output was the inconsistency of the blue score. So when you look at the first, so here Q means the question that we are giving, A means the output or the response the chatbot has given us. Original answer is the answer for this particular question. So the chatbot response and original answer, although the both of them are same, but still the blue score was very less. When you look at a different question, so this is a different question and the answer is, are you asking me if I have something to prove, is same as the original answer, but here we got a blue score of 1.0. This shows that there is inconsistency using the blue score. So upon further reading on some articles, we realized that weights need to be adjusted for the blue metric based on the sentence, so that to capture the main context words and assign lesser weights to other words. So though we read a few articles on smoothing the blue score, we weren't able to come up with any smoothing parameter that was good at capturing the actual context. These are some of the examples that we calculated blue score for. Next, finally, coming to the challenges. The challenges we faced during the whole process are listed here. First is choosing the right model. We went through a research paper which discusses about various methods on building the chatbots. Then finally we chose to work with Seq2Seq with attention mechanism. We had some issues with TensorFlow 2.0 at the start. Then we used a lower version of TensorFlow, but that was taking a lot of time. So we again switched to TensorFlow 2.0 using GPU services. The next challenge was building the model itself. So there was for writing and debugging the actual code, it took us a long time. Next is executing the model, which was very challenging as it requires GPU for faster execution. So after much trial and error, we chose to use Floyd Hub. And coming to the data part, we also have chosen a subset of the total data as we were faced with many memory errors. And finally, the model evaluation using BlueScore was a little challenging as it was difficult for us to compare the context of the output with that of the original answer using the BlueScore. So coming to our contributions for this project, as we are just 2 people in the project and also we live in the same community, we got a chance to meet many times to work on this project together. So many tasks are shared between each other. And finally, we would like to thank you for this opportunity to present our work. Thank you so much.